So here's a problem that comes up often. It's a vertical circle. In this case, we have a motorbike that's traveling through a vertical loop. We want to figure out what minimum speed does the driver need to make it through the loop without falling off. What is the biker's apparent weight at the top of the loop, and which we'll call that A. And what is the biker's apparent weight at the bottom of the loop, which we'll call B. So let's start with A. So we can draw a Freebody diagram. As you can see at the top, we have a normal force pointing down, and we also have a gravity force, noted as mg, pointing down. Now, when we do circular motion, I tend to like to call towards the center as positive, and tangentially can be positive, but towards the center, because we're not really using an x and y and our directions are changing, going toward the center I usually like to be called positive. So if we look at the top bar, we can sum the forces at point A. So that's going to be the normal force pointing down in the positive direction plus the gravity force, and that's going to equal m times A. Now, because we're undergoing uniform circular motion, we know it's a special type of acceleration. We can say that the acceleration is centripetal acceleration, which we know can be found by taking v squared divided by r, so the speed of the rider squared divided by the radius of the circle it's making, or we could use omega squared, which is the angular velocity, times the radius the person is making. So now what we need to do is just substitute some of these values into our equation. So we get the normal force plus m times g equals, so m stays there. And I'm going to use the velocity squared version, since usually if you're driving a bike, you know how fast you're going, not the period of rotation of going through your loop. So we use mv squared over an r. So you have a nice relationship. We know most of these values, but it asks us what's the minimum speed. So if you think about what's going on, as this biker goes faster and faster, the weight stays the same. So this term stays constant. As this term increases, as velocity increases, the right side increases, which means the normal force has to also increase. So that means as the biker slows down, the normal force gets smaller and smaller. At some point, the normal force has to be negative in order for this equation to balance, and that point is the point when the biker will fall off. So we really want to solve for the spot when the normal force goes to 0. That's the worst case scenario. That's right before the biker falls off. At this point, they just clear the top before they touch the loop on the other side and don't fall off. So by setting normal force equals 0, we can see that the gravity force mg must be equal to mv squared over r, or basically that the force needed to keep this biker moving in a circle is completely controlled by gravity and only gravity, and it's exactly equal to that. So gravity can't do anything else. It can't make the biker accelerate off the track. So all the gravity force is being used to keep the biker accelerating in a circle. And once we get there, we see the masses drop out. It doesn't depend on the mass of the rider. And the velocity you need to stay in this loop is just going to be equal to, if we solve this, to the square root of g times r. Now the next part, so if we remember that, next part says, what's the biker's apparent weight at the top? Well, this is kind of a trick question now. Once we did part A, we know the apparent weight, which is the normal force in the biker. We solve for the case when it goes to 0. So if the biker is keeping that speed, their apparent weight is also going to be 0. Part C says, what's the biker's apparent weight at the bottom? So now I have to look at point B at the bottom of the track. And this time, when we do a sum of the forces, we have the normal force going up. We have the gravity force going down. This again is going to be equal to mv squared over r. But this time we know what some of the values are. So we said that our velocity was going to be a square root of g times r. So we can sub that in for v in our equation, and it asks what the normal force is, and we can solve for the normal force. So we get the normal force equals, let's see, mv squared over r plus the gravity force. Again, in this case at the bottom, the track itself is holding up the rider, so it's applying a force equal to the gravity force, but it's also providing an acceleration, making the rider turn up the track and stay in the circle. So it's doing both of these. So now if we sub in some of our values, we have the normal force equals, let's see, m, the square root of g times r squared is just gr divided by r plus mg. And in this case, we see that, the r's cancel out, and that in this case, the normal force happens to equal 2mg, or the rider feels, in this area at least, twice as heavy as they would feel if they're just sitting on the regular ground.